Last time we let me brief you recall what we discussed last time. So the main idea was a mathematical object which allows us to carefully discuss differential equations, Lagrangians, and related things. The object is called jet space or jet bundle in general. So in mechanics, it's of course a kind of toy example, but nevertheless the language is the same. So geometrically, it means that we have a fiber bundle over our time. So t is a timeline. Then we have some coordinates q here, coordinate t here, and in terms of coordinates, jet space is just space with coordinates q, v, which stands for velocity, or of course we have index, which I usually suppress, then v, what was my notation, v2, etc., till certain fixed order, which is high enough to host our equations. So if our equations and Lagrangians are not high derivative, then it's enough to stop at some stage. And we do not allow for non-local equations which involve infinite amount of derivatives. That's the usual setup. On this object, we have a total derivative which mimics the action of the real derivative. Etc. It takes local functions to local functions. So Lagrangians are functions on this space Jk of E, where K stands for the order of derivatives. And for Lagrangians, we have Euler-Lagrange derivative, d over dqi, Euler-Lagrange, which by new definition act like this. Etc. And I suppress indices, and if I remember correctly, it was an exercise to write this formula for generic K. It's quite easy. And the action, if we have a section of our bundle T2E, it means that in terms of coordinates, gamma star of qi are some functions gamma I of t, right? You remember we always use the language of pullback. Can you hear me? Everything is fine? Because unfortunately I have some problems with my computer, yes, so okay. I can't control that everything is fine, because last time I opened Zoom on both devices and I could see my presentation on both screens. Now it doesn't work any longer, fortunately. Okay, so we discussed this language of pullbacks, and for instance, in terms of this language, we can write the action. The usual convention is that it's an integral over dt of gamma star prolonged. When we extend this, we do what is called prolongation. We extend the section to the section of a jet bundle by the rule that, for instance, gamma star of V is nothing but d over dt of gamma I of t, right? It's the same for higher derivatives. So, and this is the formula for for the action. One can make it even more geometrical by talking instead of Lagrangian, of a Lagrangian form. So strictly speaking, this L is not a function, it's a density. But it's only important if you want to do if you want to do generic transformations on the timeline, but as we are not going to do it, it's enough to say that Lagrangian is a function, but there is a more invariant picture. Okay, and then we ended up with discussing Hamiltonian equations. So this is going to be our starting point today. So in the particular case where Lagrange function, for simplicity, an exercise will be to do it in generality. So if we have a Lagrange function which depends on only first derivatives, so on velocities, on coordinates and velocities, it's a function on our jet space. It's enough to say, well, it's enough to take actually second jets in this case, to work in terms of second jets, because equations are going to be second order. Or of course, any higher order is also fine. I mean, to take jets of any higher order. Then our equations look like this, right? In this particular case. And in general, as I mentioned, they are of second order. It turns out very convenient, and it's a very good model for studying constraint systems and gauge systems, which we are going to study. It's very convenient to reformulate this Lagrangian system in terms of another Lagrangian system whose equations of motion are of first order. In fact, usually it's much better to work with first order equations. And the trick to do it is very simple. You actually need to introduce new variable, and such variables are called auxiliary variables. So essentially what we are doing, we are extending our bundle. So our Lagrangian system is defined in terms of this bundle E, right? Let me recall you that this is a bundle where fiber coordinates are qi and base coordinates is t. So our trajectories are sections of this bundle. But now we want to build a new system where the underlying bundle is going to be a certain extension of E. So what we do, we introduce a new dependent variable. So we extend our fiber. So in addition to Q, we are going to introduce variables P. But because we want to describe same dynamics, this P is not going to be a really physically meaningful variable. It will be what's called auxiliary variable. Auxiliary variable is the one which is completely determined by equations of motion. So equations of motion for this variable are algebraic. And in this case, it's very good illustration for this idea. So we just introduce new variable and we immediately kill it by imposing, along with this Euler-Lagrange equation, we impose additional equation. We say that Pi is just dl over dv. So it's just fixes this in terms of coordinates and velocities, right? Of course, when we extended our system with these variables Pi, of course, we also have to extend our jet bundle to include to have extra coordinates, which are like total time derivatives of P. So in addition to P on the respective jet bundle, we are going to have P, dt, P, dt squared, P, etc. So their derivatives, roughly speaking. Okay, so it is clear that this system of equations on this new system, at least as a system of ordinary differential equations, is equivalent, right? Because this is just a usual Euler-Lagrange equation, and this is just new variable which is fixed in terms of the old variables. So there is nothing you can solve for it and forget about P forever, but that's not what we are going to do. We are not going to forget about it. We are going to observe that here there is dl over dv, so we can rewrite it as follows. So we do it, we dl over dq minus dt p is 0. And this, the second equation, we are also going to rewrite. And for this, we need important assumptions. So our assumption is that this equation, the definition of P, can be solved with respect to, sorry, here should be index everywhere. I tend to suppress indices. Well, maybe it's a good idea to do it anyway. And for you, the exercise will be to reinstate the indices in correct positions, but okay, I'll try nevertheless to keep them, but sometimes I forget. Okay, so the assumption is that this equation can be solved with respect to V, so that it is equivalent to V equals to certain functions of Q and P. So this transformation from coordinates Q and V to coordinates Q and P is often called Legendre transform. So the assumption we are doing now is the assumption that the Legendre transform is invertible. So you can go, so invertible means that this equation is just equivalent to this equation. So you can solve it either with respect to P or either with respect to Q. So this change of variables is invertible. And then it's a standard fact. I'm sure you saw it many times, so I'll recall that one can introduce a certain function of Q and P called Hamiltonian, which such that the inverse transformation, the inverse Legendre transform can be written like this, that Vi is just dH over dPi. So this is inverse transformation to the previous one. So exercise, because I'm sure you all had this in the course of theoretical mechanics. The exercise is to show that H is P V Pi Vi minus L of Q V P, where we substituted V with V bar of QP, which is a solution of this definition of momentum with respect to velocities. Then this is holds. So it's just a simple algebraic fact. You take derivatives and you check that this is true. Again, a very important assumption is that Legendre transform is invertible. Okay, very good. And now we can rewrite our system as follows. So we say that it is dt of P. A moment. There is also one more rewriting to be done. So let's also consider the first equation, this one, and write it in terms of coordinates and momenta. So it turns out that one can write it as dt pi equals to dh over minus dh over dqi. It's same trick. You substitute h here, you evaluate derivative, and you check that it is the same, because h contains Lagrangian, L, Lagrange function, And there is a cancellation of two terms. So it's also an exercise to check this. So to check both. Okay, so that's the first equation, just a rewriting of it in new coordinates. And the second equation, we rewrite like this. We remember that V is dt of Q, right? dt of Qi is dH over dPi. And this is exactly, so now we have two equations of first order. Now they are, well, strictly speaking, there is a third one which tells us that no, we can avoid discussing this. No, that's enough. So you see, so it was original system, the second order system of these equations, Euler-Lagrange equations. Because of total derivative here, it contained in general derivatives of second order. Then we added new variable, which is roughly speaking the redefinition of velocity, and use this variable as a new dependent variable, and replaced dl over dv with p, so we lose second derivatives, we get first order derivatives only, but now we have a doubled set of dependent coordinates. So we arrived at the following system, which is precisely these equations are called Hamiltonian equations. I'm sure you all saw it, but now we gave a careful derivation without tricks of these equations. Of course, if you do the exercise, then everything will be careful and without tricks. Okay, very good. And this system is first order. Usually it is written, of course, because it's not very convenient to always in simple situation use this jet space language, so people don't do it. So, and it is convenient just to write it in the form like q dot equal to dh over dp and p dot equal to minus dh over dq. That's how we usually write it, not to bother with this jet bundle conventions, but in order to derive it carefully, a good way is to use these jet bundle conventions to make sure that nothing is gone. So this is a Hamiltonian equation. As you know, another standard way to write is to use Poisson bracket. So one introduces Poisson bracket. This is the following map. So it's a map from C infinity of our space. In this case, E actually. E, which is given by the following formula. So for two functions of P, Q, T, G of P, Q, T, it equals 2 df over dq I dg over dpi minus df over dpi dg over dqi, right? This is called Poisson bracket. There is a subtle point which is often not discussed carefully, and I'll explain why, that there is a time dependence. So if you want a generic system, the way we arrived at Hamiltonian equations was such that these functions are functions on the respective, like on the underlying bundle, which also contains time coordinates. And in general, we know we should be able to evaluate Poisson brackets of functions which, in addition to coordinate and momenta, depend on time. So strictly speaking, the Poisson bracket is defined on this bigger space E, but at the same time, what is called phase space is just a space of P and Q. So it's geometrically, it's a fiber of this bundle E. Phase space F is a fiber of E. That is why there are like two languages to talk about Hamiltonian formalism. The Hamiltonian formalism is the one which is based on representing our dynamical system in terms of the evolution of our dynamical system in terms of Hamiltonian equations and describing it in terms of coordinates and momenta. So there are two pictures. The first picture, the usual one, like ODE picture, let's say Lagrangian formalism, is actually that we have this bundle E, which is a bundle over timeline T. So here we have QP in this case, and T coordinates, and here we have T coordinate. And there are fibers, right? Fibers of this bundle which project to points. So this is projection. And E, and the relevant object to describe dynamics in this picture is this bundle E. And then out of this bundle, sometimes we construct jet bundle, but in fact now it's unnecessary because equations are first order. So actually there is no need to use jet bundle technology, and this is another advantage of Hamiltonian formalism. The Hamiltonian formalism is a way to avoid these jet bundles, which are technically difficult, by reformulating your system in the first order form. That's kind of philosophy. Okay, and what is trajectory in this language? As we discussed, trajectory is a section. So what does it mean? Section, it's a function which takes a point on the base and gives a point in the fiber, and this happens for each point of the base. So at the end we get a submanifold here. So this is trajectory, right? One can write another trajectories like this. So these are like different configurations of our system. Whatever. And then, so this is a picture we discussed before. And then in the Hamiltonian formalism, sometimes we use different picture. So what we say, this is like phase space picture. Space picture. So the idea is to consider only one fiber. Don't introduce this bundle, not to think in these more difficult terms, and just to consider phase space. So just F. So coordinates here are in our example Q and P. And then think of trajectory as a like line here. So this is T equals 0, then this is some moment T, etc. And then it's very geometrical also, because you can write, for instance, Hamilton equation as a usual flow of a vector field. So if we pack our P and Q into coordinates, not to treat them independently, introduce unified notation for our P and Q, then our Hamilton equation can be written like this: Z dot A equals to VA of Z and in general time. So if our and these functions V are of course just right-hand sides of the Hamilton equation, right? I just combine them into a unique vector field V. So this is a standard equation determining a flow generated by a vector field with components VA on a manifold F, right? The only subtlety is that if your Hamiltonian, for instance, depends explicitly on time, so this dependence is non-trivial on time, then strictly speaking, this V is not a vector field on this manifold. There is a parametric dependence on an additional coordinate. That's why the picture in the left part, this picture, is kind of more fundamental because it immediately gives a geometrical account of this extra coordinate t, because it's just one of the coordinates on this entire space. But practically, for computations, it's of course very convenient to go to this picture, to forget about t, think of it as a parameter, and moreover, for majority of fundamental physical systems, there is no explicit time dependence. And that's why you can simply forget about it. But again, the difference is that in this, let's say, picture of differential equations, we think of our trajectory of our system as a section of a bundle, while in Hamiltonian formalism, we think of it as a floor of a certain vector field. And time variable is just a parameter, and usually one can forget about this about this time coordinate, which of course simplifies considerations, but sometimes at the same time leads to certain confusions. Okay, I hope this was clear. Are there any questions?
Maybe not.
Okay. Okay, so we just saw that if we think of Hamiltonian equation just as ordinary differential equations, then Euler-Lagrange equations and Hamiltonian equations obtained from them, of course, are equivalent, right? In the sense, and this equivalence means elimination of auxiliary variables. Because here our variables are q and t, and here our variables are p, q and t. So we are really comparing two systems with different set of dependent variables. So time is the same, but in addition to coordinates, we also introduced momenta. We introduced them, but we knew from the very beginning, when we were deriving Hamiltonian equations, we knew from the very beginning that p is auxiliary coordinate, because p is expressed in terms of other variables and their derivatives. One can even define it more formally, such an equivalence. So we say that, for instance, so there is one system, we have system of ODE. Dependent coordinates. Let's say split into Q, I, and for instance, W alpha. So suppose that we have a system of ordinary differential equations, and there is a split of dependent coordinates into two subsets, Q and W. So we say that W are auxiliary if our equations E mu of Q W, well, the square brackets usually implies that there is also dependence on derivatives of Q, because these are equations, not necessarily Euler Lagrange, these equations, that they are functions on jet space, and they depend on Q, W, and their total derivatives. So these higher coordinates on the jet bundle. That these equations imply that W alpha are certain functions of the remaining variables Q and their derivatives. So if you can, or in other words, if you can these are algebraic equations. For the moment, I'm not even saying there are no real differential equations. All these are algebraic equations. And we just analyze them. And if we carefully study this equation and find that they can be solved uniquely with respect to variables W alpha, it means that W alpha variables are just certain functions depending on other, so they don't carry any non-trivial dynamical information. They are auxiliary. So this is a definition. And of course, it means that if we now consider a new system, where only W, new system, where coordinates are only Qi and equations are E mu of Q, and instead of W, we put W bar of Q. And this new system is equivalent to the initial. And we say that this equivalence is obtained by eliminating these auxiliary variables. And the passage from Hamiltonian formalism, from Hamiltonian equations to Euler-Lagrange equations of the same system, in the case if Legendre transform is well defined, is example of such an equivalence. Or alternatively, you can add auxiliary variables. That's exactly what we did when we derived Hamiltonian equations from Euler-Lagrange equations. Okay, I hope it is clear, and I think it's a good idea to have an exercise to, well, perhaps to really handle this exercise, you will need some extra knowledge, which will come a bit later, I hope within this lecture.
Professor?
Yep.
Sorry to interrupt. Could you explain again, like the implication that you wrote? Maybe I'm confused with the notation. I didn't. Yeah.
Are you talking about this one?
Exactly. Yes.
Yes. So what I'm saying is that suppose we are given with system of ordinary differential equations, where as usual, independent coordinate is time, right? Everything depends on time, and dependent coordinates split into two subsets, Q and W. And there are some equations. Equations are some local functions on the respective jet bundle, and I denoted them as E mu. Mm-hmm. So they depend on Q, W, and their derivatives. Then we look carefully at these equations and see that they can be solved with respect to W. So W are completely determined by the remaining variables.
Mm-hmm.
Then we say that variables W are auxiliary.
Okay.
In field theory, they are called auxiliary fields, but for the moment we are talking about mechanics. And auxiliary fields, they don't have any real meaning. It's just a matter of convenience to have them, right? Because they don't describe physical degrees of freedom, anything. They are just certain, according to equations of motion, they are just certain functions of these functions W bar of the remaining coordinates and their derivatives, on the remaining variables and their derivatives. So you can eliminate them. You can consider the reduced system where coordinates are only q, and in our equations we just put w to their values dictated by the initial equation. So we obtain new system, and we say that these two systems are equivalent through the elimination of auxiliary fields.
Okay.
Did it help?
Okay. Yes, a lot. Thank you very much.
Okay, yes. Very good. Okay, so the exercise, well, maybe it, as I said, it will be clear later how to solve it, is to derive Hamilton equations for instance, L of Q, V, and high derivatives, for instance, V2 in time, at least this example, where it also depends on derivatives of higher order. We know what Euler-Lagrange equations are, how to derive respective Hamilton equations. What happens? It's not entirely trivial, but with what I'll explain later, it will be a simple exercise. Okay, good. In fact, Hamilton equations are not just equivalent to Euler-Lagrange equations. In fact, they are also variational, and as we are going to see, variational means they are also Euler-Lagrange equations for another Lagrangian. So Hamilton equations are variational. If equations arise as Euler-Lagrange or equivalent to equations, to Euler-Lagrange equations of certain Lagrangian, we call them variational because they arise from variational principle. That's also standard terminology. Variational. Okay, it's very easy to write down the respective Lagrangian, but not to confuse, not to introduce too many Lagrangians, I'll use the language of action immediately. Otherwise, we will have to introduce too many notations. And again, the reason is if we are talking about first order system, this jet bundle formalism is not really needed because it's first order, it's very simple, you don't need higher jets, and this is a huge advantage of it. So what you could do, you could actually write the action like this. So it depends on two variables, P and Q, two trajectories, strictly speaking, if it is in action, P of t, Q of t, well, two sets. And it has the following form, dt, pi q dot I minus h of pq. If you find Euler-Lagrange equations for this action, you will find, of course, that p dot is equal to dh minus dh over dq, and that q dot equals to dh over dp. Right? So that's a simple exercise. If it's not immediately clear to you, check it as an exercise. Check. So you see that we had initial variational. So this is, let's call it Hamiltonian action, and it is called actually Hamiltonian action usually. And we have our initial action, which depends on Q of t. And this was, I just use the same conventions, and it was just L of Q dot t, right? This was our initial L. And what we checked that equations of motion, Euler-Lagrange equation, determined by this action, can be extended equivalently by introducing auxiliary variable p to the Hamilton equation here. And these Hamilton equations, in their turn, arise as Euler-Lagrange equations of this Hamiltonian action, this S Hamiltonian. Of course, you can also extract Lagrangian, but then Lagrangian is going to depend on P, Q, and their first derivatives. So for Q dot, only on first derivative of Q dot, because you see P dot doesn't enter here. So equations are equivalent, and both of them are variational. In fact, one can say a bit more. The equivalence between these two systems, because both are Lagrangian systems, both are variational systems, right? Hamiltonian equations and Euler Lagrange equations, they are of the initial Lagrangians, they are both Euler Lagrange, just for different systems. In fact, one can say, in a certain sense, that they are equivalent also as Lagrangian system. So equations. So here we have also Euler Lagrange equations, right? dl over dq minus t over dt dl over dq dot. I now use usual simplified notations without using jets. So these are initial Euler. So these equations are equivalent. So this is equivalence. Both of them arise from variational principle, from action. And in fact, these two guys are also equivalent in a certain sense. In which sense? In the following sense. So if there is a notion of variational auxiliary fields. So let's say it's a definition. Of course, it's not sufficiently rigorous as a mathematical, but it can be made into a more rigorous one. So we say that variables W alpha. So we have again a system with dependent variables Qi, W alpha, dependent variables. And then we have Lagrangian, depending on them. QW, again, square brackets mean that there is also dependence on derivatives. And we say that W alpha auxiliary, but auxiliary for Lagrangian, not for equations, but for Lagrangian. Auxiliary variables. If the Euler Lagrange equation, delta Euler Lagrange of L over d W alpha, this equation is equivalent to W alpha equals to W alpha of Q. So it's, of course, this looks exactly the same. So W alpha is auxiliary variable for if you only consider, if you are only interested in equations in equations of motion. But you see, the condition is stronger. It says that it's not just that equations of motion can be solved with respect to W, but it says more. It tells us that equations of motion for W can be solved with respect to W. It's a much stronger condition. Because Euler Lagrange equations, they have same index, right? There is the same number. They are one-to-one with our coordinates. And what we require now is that equations, those Euler Lagrange equations, which arise from which are associated to W, which are precisely these ones, that they can be solved with respect to W. Then we say that W are auxiliary fields for this Lagrangian system L, for Lagrangian, not only for equations of motion, but also for Lagrangian. It's more restrictive notion. And then it turns out that Lagrangian L, we say that Lagrangian L initial, or Lagrangian system determined by QW is equivalent to Lagrangian system with Lagrangian L reduced, which is Q and W bar of Q. So you see the second system, the first system has dependent variables Qi, W alpha, and the first system, and the reduced system, the second one, only Q. So these two systems are, they have different set of dependent variables, but still they are considered equivalent as Lagrangian system. Of course, it is clear absolutely that they are equivalent in the same sense of elimination of auxiliary fields as equations of motion, but there is more. Also, we say that they are Lagrangians, they are equivalent. So you see, there are two different things. They are related, of course, closely, but still they are different, and it is important to understand the difference. So we can speak about equations of motion, and we can speak about Lagrangians. Of course, Lagrangian give immediately equations of motion just by taking earlier Lagrange equations. But not all equations arise from Lagrangians. So it's a special class of equations. This class is called variational. These equations which arise from Lagrangian. And for this restricted class of systems, of Lagrangian systems, there is also a notion of auxiliary fields, and there is a notion of equivalence of Lagrangians, which allows to compare systems which have different set of dependent variables. Is it clear, or there are questions? Are there questions?
For me, it's clear.
Okay, and let's get back to our example, our main example. So this is precisely the case for the Hamilton action and for the initial usual Lagrangian action. Let's check it. So let me remind you. So this SH is dt pq dot minus h. So and let's try to see that p is indeed auxiliary variable. Of course, we know that p is auxiliary variable for equations of motion. But now we are going to check that p is an auxiliary variable at the level of Lagrangians. Indeed, so let's consider equations of motion, Lagrange equations. Sometimes we just write them as a variational derivative of the action. That's also standard notation. So dsh over dp, let's put index to be more careful. Pi, what it gives us? It gives us q dot I minus dh over dpi, right? This is 0. So these are our equations. But let me remind you that this is precisely the formula for inverse Legendre transform, because this is velocity, qi is, so if we switch back to this language, so what we have here, we have vi minus dh over dpi equals 0. So this is inverse Legendre transform, and we know that if it is invertible, but this was our assumption, then it is equivalent to pi TL over dvi, right? It's just the inverse transformation for some function of q and v, and we know the formula for this function. So the condition is precisely satisfied. Look at the definition. The Euler Lagrange equations obtained by variation with respect to w is algebraically solved with respect to w. So we come here, what we see, equations obtained by varying with respect to p is solved with respect to p, because we just equivalently, we have equivalently rewritten it in these terms. So P equals to dl over dv. So conditions are satisfied. So what we are going to do, to put, you see, like here. So what we do inside the Lagrangian, we just replace our auxiliary fields with them expressed in terms of other variables, and we arrive at equivalent action. Let's do it. So we take our, so what we write our S reduced now, which is SH, where we substitute P. So it's integral dt. So P is what? dl over dv. Well, v is q dot because I don't use jet language. So here I used v only to make a link with what we discussed before, times q dot I minus what? H of P P expressed as a function in terms of Q and V. So it's H of TL dV Q, right? But what is this? This is precisely the Lagrangian. dt L of Q dot, well, general T. If you go back to the exercise about Legendre transform, you know that you can express back Lagrangian in terms of Hamiltonian by this formula. So we got back our Lagrangian. So precisely the initial action in terms of Lagrange function L is obtained from Hamilton action by eliminating auxiliary variables P. And the important point is that these variables P, they can be eliminated, which means that Legendre transform is invertible. This is a very important assumption for the equivalence of these two and for this procedure to work. Okay, then one more. And the constraint system we are heading to are precisely the ones where this assumption is violated. And they are, of course, very interesting, as usually happens when you violate some assumptions. Okay, and the last example of this equivalence, which is, okay, which can be thought of as a like variational method to derive Hamilton equations immediately in terms of Hamiltonian action. So suppose again that we are given with L of Q and V. Well, let me for the moment use this Q dot convention. Well, in general T, but I suppress time. It's not important for these considerations, but everything can depend on time. Okay, and of course we have our action, which depends on Q, and this is just L of Q dot, right? So there is a trick how to immediately derive Hamilton formalism in case if Legendre transform is invertible. In fact, if you look carefully at definition of auxiliary fields, you can kind of guess what you have to do. So what you have to do, you introduce new variable P, new variable, and let's try to cook up a new Lagrangian, new variational principle, such that this one is reproduced by elimination of auxiliary fields. This is in fact simple. It is difficult to guess Hamiltonian action because it involves this tricky Legendre transform, but it's easy to guess something else which is almost as good. New variable. So let's do the following trick. Let's consider new action of Q, not only this, and also new variable V. I forgot about it. P and V, new variables. And yeah, let me put indices not to confuse you. So Q, P, V. And this has a very simple structure. It will look like this, dt. So pi q dot I minus vi plus L of q and v. Do you see the idea? So let's look at equations of motion for this system. When we take equations for p, so we take a variation Euler-Lagrange derivative with respect to p, we get that v is just a q dot. So if we substitute it here, we get the usual action, the initial one, because you see, but still there is this variable v. But if we vary with respect to v, you see that the equations can be solved with respect to p, because equations are going to look like p equals to something. So let's write down equations of motion explicitly for this action. So the very first equation is vi equal to q dot I, right? This is obtained by varying with respect to p. Then the next one is obtained by varying with respect to v. What it looks like? It looks like pi is equal to dl of qv over dvi, right? And then the last one is if we vary with respect to q, this is something like minus p dot I plus, well, actually, it doesn't depend, it's 0, right? Oh, no, sorry. This is a mistake, of course. It is plus dl over dq is 0. Look, so these equations, let's concentrate on these two. They are obtained by, this is obtained by varying with respect to pi, and this is obtained by varying with respect to vi. And but this is solved with respect to v, this is solved with respect to p. So it means that these variables pi and vi are auxiliary. And by now, you probably see that the idea is very simple, right? So p is kind of Lagrange multiplier, which tells you, which implements the constraint that v is q dot. But in fact, it does it in such a way that both p and v are gone, and we are back to the initial Lagrange. And also the equations of motion for this action look pretty much like equations which we used to derive Hamiltonian formalism, but now they are just equations from of this simple equations of motion of this simple action. So let's eliminate p and v. So if we put v equal q dot, then this term disappear, right? So we can forget about it. But what we need to do, we need to put, if you put, sorry, just one moment. So what we have to do, yes, right. So we look at this last equation, This is precisely the definition of Legendre transform. No. Sorry, I got confused. So this is the definition of Legendre transform, this one, right? It's P equal to dl over dy. If we assume that the Legendre transform is invertible, this can be solved with respect to V. Yeah, I think I'm a bit unclear. Let me try to repeat, sorry. So one thing which is very simple. If there are equations which are obtained by varying with respect to P and with respect to V, and they are solved immediately, they even appear in such a form, explicitly solved with respect to V and P. If we substitute it back, the first term disappears, and in the last term, instead of V, you get Q dot. So you reproduce, so this reduction reproduce you back this action. So this is elimination of PV. But in fact, there is another one. So this is, let's say, first reduction. But there is another one, second reduction, which is to eliminate just V variable. Let's look at, again, let's look at the equation which is obtained by varying with respect to V. It is this equation, right? Let me rewrite it. Pi equals to dl over dvi. If Legendre transform is invertible, then this is equivalent, as we already discussed, to Vi equals to some V bar of P and Q, right? What does it mean? It means that equations arising by varying with respect to V can be solved with respect to V. This is precisely the definition of auxiliary field. So you see the condition that V is auxiliary field for this action is precisely the invertibility of a Legendre transform. So if you assume that Legendre transform is invertible, we can just plug it back, right? So what we do, we S like 2 reduced is what? It's this action, so P Q dot I minus V bar of P Q Pi minus L of Q V bar of PQ, right? And this is exactly Hamiltonian action. Right? Because the expression in parentheses is just a Hamiltonian by definition. So you see, it's easy to guess. It's kind of difficult to guess Hamiltonian equation if you don't know them, but it's somehow natural to write down this section. From which you can derive Hamiltonian equation just by eliminating velocities V. And this action is, of course, well known. It is so-called Ostrogradsky action. Well, strictly speaking, the Ostrogradsky action is this action for high derivative systems. And that's exactly, let me recall you the exercise. So, which we discussed. So exercise is to now let me reformulate it. Construct analog of Ostrogradsky action for L, Q, Q dot, Q double dot. Well, in fact, same goes for any order of derivatives, but suppose for simplicity that Lagrangian depends on velocities and accelerations. Try to guess what the analog of this Ostrogradsky action is. And second point of, well, let me do it another exercise, which was before, so repetition, repeat. Try to derive Hamiltonian formalism or analog of Hamiltonian formalism by eliminating velocities and accelerations. So to bring to starting from this action to such a reduction, which brings you to equations of Hamilton type. That's maybe a bit difficult problem, requires some thinking. So I put star here. Okay, very good. So we played a bit. We understood the relation, better the relation. We understood better the relation between Hamiltonian formalism and Lagrangian formalism. And the point of view which I am trying to advocate for the moment is to think of Hamiltonian formalism just as a special Lagrangian formalism. The special Lagrangian formalism where equations have special form and are first order. That's a very big, because then you don't have additional concept. It's just, you don't need to simplify understanding. Sometimes, of course, when you work with Hamiltonian formalism, you tend to forget about this and concentrate on something else and interpret it differently. And indeed, practically, it can be very useful. But from the conceptual point of view, a good idea is to think of it as a special instance of usual Lagrangian system, where Lagrangian has a very, very special form. Okay, so let's nevertheless talk a bit about Hamiltonian formalism, because we need to understand it slightly more geometrical, in a slightly more geometrical way. You have a course, well, some of you have a course on symplectic geometry and deformation quantization, if I understand correctly. Do you have it in this semester, right?
Yeah, yes.
Yes.
Yes,
Okay, so I can be very brief. So what we are going to discuss now is, so suppose we have Hamilton formulation. So to make contact with before, it means that we concentrate on fiber, we forget about time, and for simplicity, let's assume that our Hamiltonian doesn't depend on time, and also our, well, it's probably difficult to say at present moment, but in some sense that Poisson bracket doesn't depend on time. So we can forget about time variable, and we really can think of evolution as just a flaw of a vector field on this space F. So the way we introduced it referred to particular coordinates P and Q, but in fact you can you can generalize. You can say that I can take nearly any manifold F, but what is important it's called phase space F, or before it arised as a fiber of our bundle, but it can be quite general. And in geometrical terms, this is what's called symplectic manifold, but I give a slightly more general definition. So pre-symplectic manifold, because it's also very important for constraint dynamics. Pre-symplectic manifold F omega. So omega is a two form. So it sits here. So I use this convention like wedge. Sometimes it's the same as sometimes people use, and even more often. But for some reasons, I prefer to keep capital omega for something else, which is very important in this context. So I use this big wedge to talk about differential forms. So omega is something like half dz a dz b omega a b of z. And z now my coordinates, z local coordinates on F. So this is called presymplectic form if, so the condition is that d omega is 0. If in addition, if omega is non-degenerate, which means that this matrix is invertible at any point, non-degenerate, it's called symplectic. And for the moment, we, strictly speaking, talked about our fibers were symplectic manifolds. So our phase space is a symplectic manifold. Okay. We call, if there is a vector field, V, a vector field on F, it means that V is equal to V A of Z d over dz A. So it's a first order differential operator, or alternatively, you can think of it as at each point you have a tangent vector. We call that V is Hamiltonian. If I V omega plus dh equals 0 for some h. So if there is a function h such that if we substitute vector field v into omega, it is d of such a function, then we say that v is a Hamiltonian vector field and h is a Hamiltonian. Well, unfortunately, too many Hamiltonian, but that's how people call it, is a Hamiltonian, or let's say Hamiltonian function. But for short, of course, people say just Hamiltonian function of V. So if this equation is satisfied, so V is Hamiltonian, if there is such H that this equation is satisfied. So small statement, let's say proposition. So if Lie derivative, Lie V of omega is 0, it follows that V is Hamiltonian at least locally. And exercise is to prove. At least locally means that, in fact, at some stage you'll need to use Poincaré lemma, which holds only locally, or you need to assume that certain de Rham cohomology of manifold F is empty. But it's a very simple statement. And let me also do expression in coordinates. So in coordinates. So what does it mean? It means that V I omega ij plus, oh, sorry, I use ZA. It should be different indices. VA omega AB plus dh over dz b equals 0. This is, of course, this equation. And another statement. So if f omega symplectic, so it means that omega is invertible, then any h, any function h, defines VH, which is a Hamiltonian vector field VH such that IVH omega plus DH equals 0. So in other words, if there is a function, for any function h, there is a, in fact, a unique Hamiltonian vector field such that h is its Hamiltonian. But this happens only if omega is invertible. So if omega is not necessarily invertible, then any vector field which preserves, in the sense of Lie derivative, which preserves omega, this two form, has a Hamiltonian. You can find h such that this equation is satisfied. Of course, strictly speaking, it's true only locally. But there is no way in general to construct a vector field. If you this equation can't be solved in opposite direction in general. So if we have h, it doesn't necessarily, we don't know how to construct v such that this whole, such v could simply not exist. But if omega is invertible, it's clear that you can just solve this equation with respect to v, and this solution is called VH. People say that it's a Hamiltonian vector field with Hamiltonian H. Okay, and now let's introduce Poisson bracket in this more general geometrical setup. Poisson bracket. We can introduce it like this. So for Poisson bracket, it's a map from C infinity F times C infinity F to C infinity F, right? And it, of course, it exists on if. So assumption is omega non-degenerate. So in symplectic case, it exists. Otherwise, only partial version of this structure exists, and we are not going to discuss it. So if omega is non-degenerate, then one can define Poisson bracket, namely for two functions fg. By definition, it is minus vf acting on g. Or equivalently, you can write it as minus substitution of vector field vf into dg. And then you can also, because remember that dg is minus I vg omega. So it's I vf I vg omega. So this defines Poisson bracket because we know that any function gives rise to a vector field. So to a Hamiltonian vector field associated to it. So it's a definition. And in coordinates, it can be written as fg G equals to df O dz A omega A B O Z dg over dz B, where this is inverse of symplectic structure. So omega AB, omega BC equal to delta AC, because these are functions of Z, and this should happen at any point. It's a bit, it's very useful to use the same letter, but sometimes don't be confused. So if indices are up, it means it's inverse matrix. It's a bit counterintuitive if you are used to like conventions in general relativity. Well, strictly speaking, for the metric, it is the same, but don't think that these indices are raised by any metric. It's just a convention for inverse metrics. And let's formulate the properties, which are going to be an exercise, which are going to be the exercise. So check the following properties. Properties of Poisson bracket. So of course it's obvious that it is antisymmetric. So Fg is minus Gf. Then there is Leibniz rule. Fgh is Fgh plus Gfh. And then this is almost trivial, but the one which requires a bit of work is the Jacobi identity. Which is Fgh plusGhf, so cyclic permutations, Hf G0. So this is, of course, the standard Jacobi identity, just like in Lie algebras. So in particular, if we consider functions on our manifold together with this operation omega, it's a Lie algebra. This operation Poisson bracket, it's a Lie algebra. Right? So what is important in Jacobi identity is that in fact it's a consequence of the fact that symplectic, that remember, we assumed this in the definition of symplectic manifold, we assumed that omega is a closed to form. Exactly this condition results if omega is invertible, and you can define Poisson bracket, and then you observe that this condition is a consequence of the equation that d omega is 0. Okay, good. Then let's also see how Hamiltonian action can be written in these more geometrical terms. For this, we need to solve this equation, in fact. So as we just discussed, d omega is 0. So in coordinates, it means that dA omega BC plus dB omega CA plus dC omega AB is 0, right? So it's just coordinate rewriting. And we know, using Poincaré lemma, that locally, again, at least locally, omega is d chi, where chi is a one form on our manifold. So it means that omega AB equals to dA chi B minus dB chi A. And our chi is chi A dz A, right? So this chi is called symplectic potential. Potential. Of course, it's not unique because chi plus df, where f is any function, if we apply d to this, it's just d chi because d is nilpotent, right? So the ambiguity in chi is that we can add to chi any closed one form. So there is an ambiguity in chi, but we need to fix this ambiguity in order to be able to write down action. So in general, this chi exists only locally. So in general, it means we can't write down action globally. But let's assume that chi exists globally. It's an interesting story if it does not. But in usual examples, it does exist. So let's assume that chi exists globally. Then the action can be written in the following form. Hamiltonian action can be written like this. It's integral dt of chi a of z dot a minus h of z. When you, and this is an exercise, derive equations of motion, which are going to look like this. Z dot a is equal to Poisson bracket Z a with h. So again, just Hamilton equation. Hamilton equations. And another exercise. Show that if we replace chi with chi plus df, so we choose another chi, then obviously equations are unchanged because they don't depend on chi, but the action gets a boundary term, leads to a boundary term. What is boundary term? It's when under the integral sign you get a total derivative. So if you evaluate this action on the interval from t1 to t2, you get the respective contributions from the boundaries. And this is in fact becomes very important if you study systems with boundaries, etc. In many situations, it is very important. For the moment, we don't pay much attention, but still, it's a good exercise to check it. So you see somehow the action knows more about the system than just symplectic structure and Hamiltonian, because it also knows these boundary terms, which are important in set, etc. But traditionally, when people talk about Hamiltonian systems, they usually define this in terms of just minimal data of symplectic structure and Hamiltonian. But perhaps better way, if you want to define everything in full generality, is also to specify symplectic potential, because from physics point of view, it is an important data things depends on what the symplectic potential is. Sometimes do not depend, but sometimes depend if you have boundaries. Okay, let me just, I think we are almost out of time. So let me just announce what we are going to do next. Next, we are going to consider more general systems than Hamiltonian systems. And these correspond to the situations. They arise, for instance, from the situations where Legendre transform is not defined. Do you remember that in the very beginning, previous time, we considered relativistic particle. Relativistic, what's going on? Something wrong? I see what's the problem. Yeah, we considered relativistic particle. With Lagrangian action beta depending on x and lambda, and which was integral over dt x dot squared over lambda minus m squared lambda. If you try to play the game which we played today to find Hamilton formulation, you are going to fail because you can't bring, by equivalence transformation, you can't bring this action to the form or to the Hamiltonian form. But what you could do, if you remember, you could write like more general Hamilton action, which depends on such variables and which has the structure dt p mu x dot mu minus lambda over 2 p squared minus m squared. You see, well, it's a very strange action at first glance because you don't see Hamiltonian. There is no function of phase space variables. But there is a strange term like this. And also our variable, it's not a symplectic manifold because our coordinates do not come in pairs. You see, there is a pair of x and p, which seem to be canonically conjugated. But there is an extra variable lambda, which does not have its associated momenta. And this is the first example of a constraint system. So lambda is called Lagrange multiplier. Because its role, if you vary this action with respect to lambda, you will see that this function must be 0. And this p squared minus m squared is a constraint. And Hamiltonian is 0. In this case, in fact, that Hamiltonian is 0 has to do with the fact that there is a reparameterization invariance time. So the evolution along this time, which is written here, because this t has nothing to do with 0 component here. It's better even to call it, let's call it tau, not to confuse. So it's an example of Hamiltonian-like system which has different structure, more general structure. There are constraint systems when there is a Hamiltonian, and also there are constraints. And this is a more general setup. And we are going to study these systems in the next, during the next lecture. So thank you very much for the attention. Are there any questions?
For my part, no.
Okay, good. Then try to do exercises. We already have quite some of them. And I hope Dmitry will help you to with studying these exercises. Okay, thank you very much, and see you next Friday, I suppose.
Professor, maybe before we go, could you share the lecture notes you told us about the previous class?
Oh, yes. Do you want recordings of lectures or lecture notes?
The lecture notes.
The lecture notes. Okay, I will, but let me warn you that it's not one-to-one. I changed slightly. Well, of course, morally it's the same, but it's not one-to-one. I don't closely follow the notes. Also, I want to update them because I'm not happy. But of course, these are going to be helpful. So I'll send you to our joint Telegram chat.
Okay, thank you.
But be careful. Also, there are typos. Maybe some conventions can be different. So it's not like a full-scale book. But still, it can be useful, I hope.